commitment
I
from
like
the
this question. I think there's some good things you can learn from this question, yeah?
yeah.
So this question is about a triangle, yeah? A, B, C. It has to be acute. And there's another triangle inside it somewhere, yeah? That's also acute. Yeah? And the goal is to show that the area, so the area of the big triangle is S, the area of the small triangle is S1. That S on AB plus AC is always bigger than S1 on A1, B1 plus A1, C1. Yeah?
And the thing does work with coordinate geometry.
Yeah, I think some of the simpler cases work with coordinate geometry. Okay. But I feel like the observation I made on Monday is enough to solve this problem, yeah? I don't know if you remember the observation I made. But anyway, first of all, it's obvious that it doesn't matter where B1 and C1 are, right? So you might as well just assume B1's over here and C1's over here. Yeah?
Yeah.
Because if you switch them, the lengths don't change and the area doesn't change, right? Yeah?
Yeah.
Okay. So there was one observation I made that was kind of interesting. Like if you look at this formula, right? This is like these are all things about the big triangle. These are all things about the small triangle. Yeah.
Yeah.
So, for example, one situation that we know how to compare them really well is if they were equal triangles. Yeah, you know that they have to be equal. Yeah.
Yeah.
And we also know if there were similar triangles, this would also be true. Yeah. See, because what
If
does it
they're
mean to be
similar.
similar? Yeah. It means that the AB is in some ratio to A1, B1, right?
Yeah.
And the point is it's the same ratio for all the A1, C1.
The side lengths will be the same ratio, so the area will also be in the same ratio, and
So
so
the area
it's the
is in
same fraction.
the squared, yeah?
Yeah, it's the same fraction.
So basically it's the same fraction times r, right?
Yeah.
So the point is if the ratio is big, if the bigger triangle is similar but bigger, right? The ratio is bigger than 1, so this will be bigger than that, yeah?
Yeah.
So it's true if similar, yeah? Does that make sense? Okay, so there's a condition where A1 has to be inside the triangle, yeah? But I want to remove that condition, yeah? So I want to let A1 be anywhere as long as all 3 points is not like all three, like it's not the same triangle, okay?
Yeah.
So it's obvious that it's equal if they're the same triangle, yeah?
Yeah. Yeah. That's,
Okay.
and also similar triangles.
So we're gonna, similar it's not equal, okay? Similar it's bigger, yeah?
Oh, your ratio square to ratio.
Yeah. The point is it's a square up the top and there's only a linear at the
And
bottom,
normal
yeah?
at the bottom.
So we want to remove A1 being inside as a condition, yeah?
Yeah.
Okay, and replace it with the triangles not coinciding. Okay. Okay, so the fact it can be similar, it allows you to do a lot of cool things, okay? So for example, if this is A1, right? Yeah?
Yeah.
You can make it similar, yeah? So you can draw it like here, yeah?
Yes.
And make it similar. Yeah?
Oh, and then you can add a little bit and then say it's
So
not.
basically what that means is the outside triangle, this property number thing, this label, right? For the big triangle is bigger than this label for the red triangle, yeah?
Mm.
So what I'm saying is it reduces the problem from the general case to a more specific case. Can you see?
But can't you split it into similar triangles? Like the original triangle, can't you split it into smaller, similar triangles?
So you need to split it into a triangle similar to the big one, yeah?
Yeah.
Okay, but you're not really appreciating what I'm saying, okay? You're actually focusing on a minor piece of this, okay?
Okay.
You gotta listen. Look, so the point I'm trying to make is right.
Mm.
The big triangle has this number is bigger than the red triangle with this number, yeah?
Yeah.
Because they're similar, yeah?
Yeah. If the similar triangle is bigger than the other one, that means that the first one is obviously bigger.
Yeah, exactly. So it reduces the question to showing that the red number here is bigger than the blue number here, right?
Yeah.
Okay. But this new question is a more it's a different case now. Can you see? So look at the new question now. So if you have the red one, right? It looks like this, yeah?
Yeah.
So basically it's like saying you can assume B is equal to B1, yeah? Do you understand what I'm saying?
Mm. Mm-hmm.
Because before B could be anywhere, yeah? But basically you can assume it's equal to one of the edges and one of the endpoints, yeah? Which is obviously a simpler case. And you can discover with your chord bash that it's much easier to chord bash when B1's fixed at B, yeah?
And then you can do the same thing as C, potentially.
Sort of. Okay, so it depends on what the actual triangle is, but if you look at it, right? Even if you look at this shape, yeah?
Yeah.
Like, look at this shape. Let me draw this in blue, yeah? Okay.
Yeah.
So you want to show that this quantity for the red triangle is bigger than this quantity for the blue triangle, yeah?
Yeah.
But you could also draw like another intermediate triangle, okay? So you could make another triangle. So make this the same line on the blue line, yeah? And make this black line along the red line, yeah?
Yeah.
So then you can have the red triangle has this number bigger than the black triangle that has this number, right? Yeah?
Mm.
And then the black triangle is bigger than the blue triangle. See what I'm saying?
Oh.
So that changes the case to two cases. So now we've changed that case into the case where basically it has to go along the side, right? That's the red and black triangle, yeah?
Yeah.
And the black and blue triangle is like the case where A1 is equal to A, yeah? And B1 is equal to B.
Yeah.
Can you see that?
Yeah.
So actually we're reduced to showing it for these special cases. Can you see that?
Yeah. And then now we have a simpler
Yeah.
chord bashing problem.
Just by drawing some lines, yeah?
Yeah.
So I guess a general construction is you could just always take this one all the way out. So you can assume B1 is equal to C1, unless okay, we can maybe make this a little bit more precise, yeah.
Mm.
Let's have a look. So we have a big triangle, yeah?
Yeah.
Inside there's a B1 and C1. So the possibility is that this angle could be slanted that way, or it could be slanted even more acute, right?
Yeah.
So can we make some cases? So for example, we have one that's like going this way. Like it's not as acute, yeah?
Yeah. Mm.
Okay, and then this one could be like, it could be more acute, yeah?
Hmm.
Or it could be like um, more steep, yeah?
Mm.
Does that make sense? So basically it could be
Yeah.
more steep or it could be more acute, yeah? So
The closer you get the right side in, the more acute.
yeah. Yeah, so maybe we can just pick a case and deal with it, yeah? So if it's more like acute on this side, yeah? And let's say it's more acute. Can it be more acute on both sides?
That makes it obtuse though.
Does it?
Yeah.
Is that obvious? So if this was the parallel line, yeah?
Yeah.
Yeah, that would make this angle too big, right?
Hmm.
Well, would it? So it would make it bigger by this amount, wouldn't it? So make it bigger by this amount, yeah?
And that amount. Yeah.
But that might not make it too big, will it? Depends on what those are, doesn't it?
Yeah. Can't make them both too acute.
Yeah.
That's what we get out of this, which is not much really.
So I think it can still stay acute, but
Not too much acute.
that gives you the case where A and B. See, if you draw in the red triangle there, that gives you the case where B and C are the same as B1 and C1, yeah?
Hmm.
Yeah. Okay. What if this? Maybe I'll draw the other line in black or something. So what if this triangle now was outside this triangle, like it was like this, yeah?
Like outside?
So like it's not power. It's less steep. It's not acute. It's not as acute. But it was like that, yeah.
Oh, okay. So barely acute.
Yeah.
Yeah.
So what you can do is you can extend this one a bit further, right?
Yeah.
To make it come down here. Yeah.
Okay.
So you still reduce to the case where C is equal to C1, yeah.
Hmm.
Yeah.
Yeah.
Actually, you don't really need it to be similar. You just need to keep drawing smaller triangles, yeah? I guess that's one
Yeah,
of the
and make
points.
it easier to do.
Yeah, it just made it more obvious when you knew it was true for similar already, yeah?
Hmm.
Because, yeah, how do you get from blue to red, yeah? It's because it's similar, yeah?
Yeah.
And then we're trying to get from red to black because it's degenerate, you know?
Hmm.
Yeah, and see, if you focus on this again, you can get this thing where A is equal to A1 in this triangle here.
Mm-hmm.
Yeah, is it possible for both angles to be steeper? It's not, right? Like, the angle inside is always bigger than this angle, is that true? Like, this one's always bigger than that one?
David said, "Can you code bash it?"
Huh?
David said, "Can you code bash it?"
I don't think you can chord bash it that
I
easily.
don't think you can do the whole thing, code bashing.
I think you can definitely chord bash it once you've reduced it to the cases. Yeah? Like,
Hmm.
if you reduce it to this case, and there's one more case, so there's another case where A1 is equal to A, right? It's this case, yeah? It's like it's like that case. Yeah?
Hmm.
Yeah. So we've done it for the case where one of them is acute, one of them is steeper, one of them is not as steep, and we did it for the case where both of them are less steep. Is it possible for them to both be more steep? Does this angle always have to be smaller than that angle?
Um,
It doesn't, right?
yeah, no, I don't think so.
I mean, it doesn't. I mean, does it have to always be bigger than that angle? It doesn't, right? It can be bigger or smaller.
Yeah, you can move the side along to change the angle.
Yeah. So once it's similar, it's equal. You can then move it in and out to change the angle, right?
Yeah.
Yeah. So you have done this question, David, but you didn't get it, did you? I don't think you did. I looked at your answer. Okay. Yeah. So it could go on the outside, I guess. It could go up and then like maybe meet. Maybe it'll like meet right up here or something, yeah? So maybe it'll meet like maybe like here. There's like another triangle here. Yeah, but the point is as long as the A is inside the triangle, right, you can always kind of draw a similar triangle to cut it out. Yeah?
Yeah.
So
But the thing is, the big triangle has a bigger thing than this similar triangle, right? As we said. So doesn't that mean that even if the triangle inside is somehow bigger than the similar triangle, then it doesn't necessarily have to be bigger than the outside triangle?
yeah, so if it's inside it's fine.
Well, I just mean back this one.
So if it's really steep, then what happens? You can draw this kind of similar triangle. Yeah? Okay. So if it's really steep, yeah, so if it's really steep like that, you can do that and then you can break it up into like this and this. So you're back into this case again, right? Okay. What if like one of them's more steep and the other one's not as steep? So this one's less steep, but this one's more steep. You know? Then you can make a similar triangle like that. Okay, so you're in that case here. Now, of course, if they're both less steep, you almost run into trouble getting obtuse stuff. So you get stuff like this. So I guess what you can do is you can make this like that. So you have the case where the endpoints are the same, and then you could probably break it up like this. So that's now we're in this case. Yeah. Yeah. So basically, we got that. No matter how the black triangle is written, you can always break it up into basically these two cases.
Oh, there's simple code bashing and another simple code bashing.
Yeah, but
Wait,
yeah.
isn't that the kind of the same thing? If when it's rotated. So technically, isn't it the same case?
Well, is it? So, I mean, this length doesn't rotate. You know, like the sum of these two lengths don't rotate to the sum of these two lengths. But if you phrase the area differently, it might work. Yeah. So if you phrase the area in terms of so if they have a common base, then it's just the ratio of their heights. And here they have the same height. It's the ratio of their base.
No, like I'm not like for code bashing. Those two cases can be the same. Like you can do it in the same. Like you could just say as previous cases.
Yeah, so they look similar, but how can you make them exactly the same? Yeah. Okay.
Because the top of the triangle goes down to the A, B, and A dash is arbitrary.
Yeah, you can use the same
That would be the
coordinates,
same
but
as
you'll
C
get
dash.
different formulas. Yeah. Well, unless you have an idea. But actually, just for this case, there's actually some nice geometry in this case. It actually it has the same thing that we had before. Actually, we had this thing came up once before with the basketball. Okay. So it's kind of interesting. So I mean, let's look at let's look at this. Yeah. So let's label this side small x and let's label the big side big X. Yeah. Yeah.
Okay.
Make this small y. This is big Y. Yeah. So what do you see we need here? We need basically we need can you see basically we need oh by the way, so can you see because they have the same base, yeah? Can you see the ratio of the areas is just little x to big X? Yeah.
Oh, sorry, I was muted. Yeah.
Yeah, so the area, so S on S1, right, is just equal to X on X. Yeah? Oh, I see David typing a lot of stuff. So people say use triangle inequality but never spell it out. I don't understand. So this is bigger than that. Okay, so can you see that X on X is the ratio of the areas? Because if this is the same side, they have the same height from this base, right?
Mm-hmm.
If they're the same height from this base, yeah,
Yeah.
that means the base determines the area. Okay?
Yep.
So the ratio is just the ratio of the bases, yeah?
Hmm.
Okay, and you need to compare that with AB plus AC on A1B1 plus A1C1. Yeah, so that's just X plus Y on little x plus little y, yeah?
Hmm.
Okay, and you need to show that that's bigger, yeah?
Yeah.
Okay. So this is actually like a basketball thing, yeah?
Oh, come on.
Huh?
No, David typing. It's just, I don't know. No, it's okay. It just spam came up on my screen. My laptop is half crashing.
Oh, okay, yeah, my laptop crashes too sometimes. So basically, remember we had this thing where like, maybe it's more obvious when it's little x on big X, but the point is it's like if you're shooting basketballs, right? Yeah?
Mm-hmm.
And
Trajectory?
no, you're just the percentage of shots made, yeah?
Okay, yeah.
Okay, I guess it makes more sense the other way around. But if it's like X on X, that means you've shot more than 100%, right?
Yeah.
Yeah.
Which
So that means
was kind of,
if you add the same number to both the numerator and denominator, it says what happens if you shot an extra if you shot 100% and you're averaging, yeah. So it's like you're thinking the next few shots you made them all, right? That'll lower your percentage, right? Because your percentage is higher than 100. Yeah.
yeah. Yes.
Yeah. So I guess the more general version of that is if you're shooting the ball, as long as
And you shoot.
with a lower percentage, yeah. So yeah, you're right. So if basically the y on the y, yeah, is
Mm-hmm.
less than x on x, right? Yeah.
Yeah, so if you add stuff to it, it's still gonna be, it's
Then
gonna get
it's
less.
gonna be less, right? Because you have a
Yeah.
smaller shooting percentage, yeah.
Yes. Oh.
So this is all you have to show, yeah.
That'd be funny though if you explained it with that analogy.
Yeah. Yeah, but you just cross multiply, you get that, right? But I liked speaking in terms of that one because I thought that was cool at the time. Um, so basically, can you see what x on x is, right? Okay. So x on x is like if you made this line parallel, right? And this is like your
Yeah.
y naught, yeah? So x on x is equal to y on y naught, yeah? Does that make sense?
Yeah.
So I guess what you're basically saying is that y naught has to be Smaller than y. Yeah?
Otherwise, the percentage keeps, or the fraction in this case, keeps dropping.
Yeah. Does that make sense?
Yeah.
So is it obvious that y naught has to be smaller than y?
I mean, doesn't the reason that we just said work for
Huh?
it?
No.
Isn't just what
We're
we
using
said
this to
work?
justify that. Yeah? We're trying to prove this. We don't know this is true. Yeah? This is like the left-hand side. This is S over S1, right? This is that over this. So to prove this, we just have to show that basically y is always bigger than y naught. Okay? Now, is that obvious? It's one of those things that it's simple enough that even if it's not obvious, we can kind of spend some time on to figure out, yeah? And should be able to figure out. Like, if you draw a triangle like this, yeah? I mean, I guess how general is the statement? Is it always true that if you have a triangle, that like any side here will be smaller than that side? That's not true, is it?
I think so. That doesn't sound true.
Well, you could have like an isosceles triangle, right? So that wouldn't be true. And then that would be longer, yeah?
Yeah.
But it can't point that way, yeah? Because it has to be parallel to this side, yeah? So you might have to relate this, so it has to point that way. Hmm.
Interesting.
Yeah, so this is where you can use the triangle inequality, right? Oh wait, no, it's not quite right. What are we trying to show? Y is always bigger than.
Oh, he said something in English. Oh,
Draw a line from A1 to AC parallel to BC. From A1 to BC. This is what that line is. That's this line, yeah? Oh, from
says he
A1
means
to AC.
AC.
A1 to AC. Like here. Yeah?
Call that point A2. Because why not? No, don't call that A2.
Alright, so what are you doing with this? X on X equals Y on A2.
Hmm.
Yeah. Equals y on okay. So what's the difference between this and what we were doing?
Because y upon because what we said before.
So you can compare y and A2C. I mean, A2C is the same as y naught. So I guess you have a 9 degrees. Uh, y is clearly bigger. Yeah, I guess we want to elaborate on what clearly means. I mean, it is pretty clear from this diagram that it is bigger.
Mate, stop with the Greek.
Okay, let's see if that argument works the same here, and let's see if that's the choking point, okay? And let's see if we can focus on that, okay? So if we have this thing here, right? It relies us on knowing the ratio of the bases. So this is like Z, and that's like big Z, yeah? So then you have like little z, big Z on little z is the area. So this is like X, it's the same for both. And you have Y and Y, okay?
Bridge.
So you
What?
have X plus Y on basically X. Plus little y. Mm-hmm. So that's that other case here, yeah? So you need that to be bigger. Yeah, I think big Y has to be bigger than little y.
Yes.
Hmm. So there's two things, okay? So there's showing this case, and it's showing that this y is always bigger than this y naught, okay? Yeah, I think this is basically like more or less obvious, just because it can't be an obtuse angle triangle, yeah? It's like the only way it can be equal to this length here, right? Is if it swings all the way around, you see what I'm saying?
Oh, come on, watch it.
Yeah, so maybe it is true in general that like if you have a triangle, right? Like this is 90 degrees here. So, I mean, you have a line. This is 9 degrees. And you have another line on this side of it, right? So it can't be here because that would make it obtuse. It has to be on this side. Yeah? So you can see this side is always shorter than that side, yeah? Like the blue line is always shorter than this line. Okay? So one way to see that is like the cosine rule, yeah? Or Pythagoras, sorry. It's the hypotenuse of a triangle with this length getting smaller, yeah?
Yeah.
So it actually has to go to the other side for it to get bigger. So this y naught is always less. So this is true, yeah?
Mm.
Okay. Okay, so we can focus on the other case now. Because the point is, if the y naught is always less, then this expression is always bigger than that expression, right? Because everything's the same except for the denominator. Okay, so we covered this case where it looks like that, yeah? And equivalently, it could also do that, yeah? Yeah. So now let's look at the case where it does that. So it does this, yeah? And you can kind of make this, you can make this length almost as small as you want. If I keep drawing these lines, yeah? Anyway, so B, C1, C, yeah? So you could probably chord batch this as well. But maybe we could come up with an argument, huh?
I shall be back.
Mm. So I want to make this whole thing Z. Make this thing little z. I guess this breaks up into two cases, huh? So if you insert a line like here, can you always do this? Maybe it's on this side. Like if you could insert a line here, so that this is equal to that. Then you have sort of two cases where it's like you get an isosceles triangle on the inside and an isosceles triangle on the outside. So this is an isosceles triangle on the outside. And here you have an isosceles triangle on the inside. Yeah? So in this case you get, so but both of this, I want to do Z on Z compared with, so we call this big X and big Y. Yeah? So this is like X plus Y on X plus little y. Yeah, and this is X plus Y on X plus X. So that might not always be possible, I guess. That length is longer. What if it was shorter? Then would it go inside?
What is that?
So this might not always be possible to do, but does it make it more obvious in these cases? Or does it do nothing? And here it's like x, y, and y. Like x plus y on x plus y. Yeah. So big X is equal to little x. Let me erase this for a second. Mm-hmm. Oh, this here would be an x, I guess. A big X. So this is a big X, yeah? So can we show, for example, that z on little z is bigger than y on little y? Yeah?
Yeah.
Yeah, see, because if that's true, right, then this is also bigger than any, if you add x to both, it's going to be bigger than this, yeah? Right?
Hmm.
If you add a positive number here, that's like the 100% thing, right? It's making it go down.
Hmm.
Can you show this on this? So this on this, okay, it's another y naught thing. That's why I drew that. So if you can draw the parallel line, yeah? Yeah. That's y naught, yeah? So you draw it at C1, parallel to AC. And this will give you y on y naught. Yeah? See that? Okay, so then y naught just has to be smaller than y, yeah?
Hmm.
Okay, but it's the same argument as before, isn't it? Remember? Yeah? Because it's an acute triangle, this hypotenuse is always bigger than this hypotenuse by Pythagoras. So yeah, in some ways the two cases are the same, yeah? It's just... Okay, so basically we didn't need this isosceles stuff. So we didn't really use it properly anyway. So basically we reduced the general case. So we saw similar triangles work, yeah? And we used similar triangles to reduce it to basically these three cases. We also generalized the problem to like A1 could be anywhere as long as the triangle is not the same triangle, yeah? Yeah.
Yeah.
So can you see that that's the beginning of a proof? So that's the solution without the write-up?
Yeah. That's where you can just start with to explain the question.
Yeah, I mean, the main step, I guess, is to reduce it to these degenerate cases. Because then even if you needed to chord batch, you could do it, right?
Mm.
It's strange because I feel like this is harder than... The way I've done it is harder than what I expect from TOT. It's just maybe I just like this method, you know? But it feels like it's harder than what I would expect. But like, can you see? But if you look at the mark value, right? This is question 2.
I mean, it's like a question 2, so.
But it went to 7 marks. Okay. So that's different. Normally,
why is it 7 marks for a question 2?
Because sometimes it could be 5 marks. So 7 marks is the same mark value as question 3 and question 4. Okay. Question 5 and 6 was 8. Yeah. Okay. Any questions, David?
It's A-level, dumbass. Okay, well done, David.
Oh, I'm lagging. I didn't even see it.
Oh, wait, no. Oh, he sent it privately. Well done.
Oh, okay. Alright, I'm gonna